Hello and welcome. Today we are diving into one of the most incredible systems inside your own body, your blood's very own, very smart delivery service. Let's get right into it. Okay, think about this for a second. You take a breath, right? That oxygen has to get from your lungs to your brain, to your muscles, maybe all the way down to your little toe. How does your body pull off that amazing logistical feat without you even thinking about it? Well, the secret isn't some big central brain directing traffic. No, it's all down to a tiny, microscopic taxi service that runs on a perfectly brilliant, self-regulating set of rules. Now, to really appreciate why this taxi is so important, we have to first get a handle on the huge problem our bodies have with oxygen in the first place. Get this, 1.5%. That's it. That's the tiny amount of oxygen that can actually dissolve directly into your blood. It's just not that soluble. If we had to rely on that alone, we wouldn't make it more than a few seconds. We obviously need a much better way. And that better way is called hemoglobin. This molecule is the hero of our story. It's that smart taxi we've been talking about. You'll find hemoglobin packed inside every single one of your red blood cells. It's a special kind of protein that has iron in it. And that little bit of metal, well, that's the absolute key to how it works. What's really important is its structure. You can basically picture each hemoglobin molecule as a little four-seater car. It's got 4 parts, and each part has an iron-based heme group in the middle. This means every single hemoglobin molecule can carry 4 molecules of oxygen. But here's the thing, it doesn't just carry oxygen, it loads and unloads it with this incredible built-in intelligence. And that's all thanks to its superpower, something called positive cooperativity. The way this works is just so cool. Imagine trying to get the first person into a really crowded taxi. It's a bit of a squeeze, right? That's what it's like for the first oxygen molecule. It's a little tough to bind, but as soon as it does, the entire hemoglobin molecule literally changes its shape. It goes from a tense state to a relaxed one. This basically opens up the other seats, making it way easier for the second, third, and fourth oxygen molecules to just hop right on. This whole process guarantees that in your lungs, where there's tons of oxygen, hemoglobin gets fully loaded up super fast. Okay, so loading up is one thing, but how does hemoglobin know where to stop, where to let the passengers out? That's where the first set of instructions comes in. It's called the Bohr effect. The Bohr effect is just a beautiful piece of chemical logic. See, when your cells are working hard, they produce waste, and the main waste product is carbon dioxide. When that CO2 gets into your blood, it makes the blood just a tiny bit more acidic. And that change in acidity, that's the signal. This is what's so brilliant about the system. The very tissues that are working the hardest and need the most oxygen, like your muscles when you're exercising, are also producing the exact chemical signal that tells hemoglobin, hey, drop the oxygen off right here. It's a perfect demand and supply system, all on its own. But a good taxi service doesn't just drop people off, right? It also needs to pick up the return fare. In this case, that's the carbon dioxide. And this brings us to the other half of this amazing process, the Haldane effect. So first, let's just see how CO2 actually gets around. About 20% of it hitches a ride directly on hemoglobin. But the vast majority, a full 70%, is actually converted into something called bicarbonate, which then just dissolves in your blood. So the Haldane effect, it describes this other side of the perfect exchange. It turns out that once hemoglobin has dropped off all its oxygen, it changes shape again. And this new shape makes it way better at grabbing onto carbon dioxide. You see what's happening? The very act of delivering oxygen gets hemoglobin ready for its next job, cleaning up the waste. It's just an incredibly efficient two-way street, a perfect taxi service. All right, let's put it all together now. Let's watch this whole cycle, this great gas exchange that's happening trillions of times a second right now inside you. No, it's really important to get this. These two effects, Bohr and Haldane, they aren't totally separate deals. They're two sides of the exact same coin. They're a single elegant process where one causes the other. Let's walk through it. Okay, you're in the tissues. CO2 is high. The Bohr effect kicks in, making hemoglobin let go of its oxygen. The moment it does that, the now empty hemoglobin is perfectly primed to pick up CO2. That's the Haldane effect. Then that taxi travels all the way back to the lungs. In the lungs, there's a ton of oxygen, which binds to the hemoglobin. That binding action then forces the CO2 to get kicked off, which is the reverse Haldane effect, so you can breathe it out. It is a perfect, continuous, beautiful loop.
And this system is so amazing, it's even adaptable. I mean, a fantastic example of this is fetal hemoglobin. A developing baby has to solve an even tougher problem. How do you get oxygen from your mother's blood?
Well, it turns out fetal hemoglobin is built just a little bit differently. It has a much stronger attraction, a higher affinity for oxygen than adult hemoglobin does. This lets the fetus literally pull or steal oxygen away from the mother's hemoglobin as their blood supplies pass near each other. It's a clever trick to make sure the baby gets all the oxygen it needs. You know, when you step back and look at the whole system, the cooperativity, the Bohr effect, the Haldane effect all working together, you just have to be in awe. It really is a molecular masterpiece. And this right here is the key thing to remember. Hemoglobin isn't just some dumb bucket carrying oxygen around. It is an intelligent, dynamic, shape-shifting machine that's constantly reading its environment and responding perfectly to make sure every single part of your body gets exactly what it needs, exactly when it needs it. This whole incredible dance of molecules is the result of millions of years of evolution fine-tuning it to perfection. It really makes you wonder, doesn't it? What other invisible, amazing marvels are humming away inside you at this very second, just keeping you going?